Thanks, Ravi. My name is Celina Mikolajczak. I am the Chief Battery Technology Officer at Lyten. Thanks so much for inviting me to speak today. Before lunch, the panel was talking quite a bit about the US space program and the space race. So let me ask the question, how many people in the audience have seen the film Hidden Figures? Maybe show of hands. Oh yeah, that's good. It's not just the women in the audience who watch this. All right. So for those that haven't seen the film, it's set in the early 1960s at NASA Langley, where computers, who are at that time literally women who are really good at math, they're doing calculations to support the various spaceflight programs. Now, one of my team members suggested that we screen this film over a few lunches about a month ago to celebrate both Black History Month and Women's History Month. And I love this film. I always find really new and interesting things in there. It's historic. I'm a feminist. There's so much to love. So of course I said yes, and we bought snacks and popcorn, and we watched this over a couple of lunches. This time while I was watching it, sitting with my R&D team, I was struck by how well this film depicts the technology development process for a significant endeavor. People have a great idea, maybe a geopolitically world-changing idea. There are lots of papers written about it. The case of the space race, there was plenty of science fiction already written about this. Yeah, and I'm also that sci-fi geek, right? Space, the final frontier, also in the 1960s. But it's not an easy thing to go do. What the film shows you is that you can achieve these things, but it's not just nice ideas, not just academic papers that get you there. It requires engineers and scientists to commit. And they commit to usually very unappreciated, unstoried, thankless, late night, work on weekends, daily grind of work. And it is a lot of work. It is a grind. Now, inspiration does show up periodically, but it's not just free inspiration. It's the result of all that grind. Now, in that film, that's depicted by the computers, the women, doing and redoing calculations by hand, engineers running wind tunnel test after wind tunnel test. And if you know much about the US rocketry program, you know the engineers were doing a lot of iterations on rockets. There were a lot of failed launches and then finally successes. I'm also, by the way, a big fan of the Air and Space Museums in town. My dad was gas turbine guy, done a lot of visits with him. My father-in-law was a satellites person. I've done a lot of visits with him. Personally, I like the Udvar-Hazy one. If you're out there by Dulles, go check it out, okay? All that grinding work also involved a fair bit of desperation. Folks were trying not to be left behind by the Russians. They were under a lot of pressure to go faster, okay? This is what a lot of us hear all the time is go faster. It meant pulling a lot of unlikely looking people into the effort. And the teams, they were not so much about individual contributors. They really were about teams that could work intimately with each other because no one person could hold the entire space program in their head. Now, if you study the space race, you know that the engineers and scientists involved couldn't just copy could copy other tech. They certainly learned from the German rockets from World War II and the Russian advances, but they really couldn't stop there. They had to create new science and new engineering. At Lyten, my job is to lead a team, not so much individual contributors, but really a team capable of working intimately together through the grind to develop that new science, that new engineering to make commercially viable battery cells and then put them into production with a new chemistry that has the potential to be geopolitically world-changing. All right, now, unless you're a battery geek or in academia, you've probably never heard of Lyten cell chemistry. It is lithium-sulfur. That means a sulfur cathode and a lithium anode. No nickel, no cobalt, no iron phosphate. Sulfur, lithium. Okay, so why haven't you heard about it? Sounds awesome, right? Well, you haven't heard about it because it's really hard. People have been trying to make lithium-sulfur work for decades, and then they've ended up throwing their hands up, walking away, and going to an easier chemistry. But people keep coming back to it, and they keep trying to solve this because this is the chemistry that allows us to electrify everything. and it lets us solve the geopolitical raw materials supply problem. Sulfur, as many of you know there's a lot of minerals guys here, is very abundant and it is cheap. If we can make this work, we don't just solve the domestic supply chain problem for batteries, but we create electric power abundance globally. Now think about that for a moment. You eliminate the whole geopolitical raw material dependencies for battery production. Not only that, lithium-sulfur is lightweight. It has the potential to push past the energy densities of traditional cathodes. So today I drive a Model 3. Someone else have a Model 3? Yeah. Those cells are high nickel cathodes paired with graphitic anodes. They have an energy density just about 300 watt-hours per kilogram. Okay? Now if you take those same nickel cathodes and you pair them with lithium metal or with silicon, you get to energy densities of about 450 to 500 watt-hours per kilogram, about 50% increase. And really, that's what the whole race to solid state is about. That's what people are trying to do. They're trying to achieve those levels of energy density. No one's done it commercially yet, not really, not at the automotive scale. However, at those energy densities, the lithium-sulfur roadmap, it's just getting started, okay? We think that achieving watt-hours, 600 watt-hours per kilogram by the end of the decade is possible, and that still leaves a lot of room for technical development. This means that we can electrify ground transportation, but it also means we can electrify aviation. We really are talking about electrifying everything. On top of that, we estimate that lithium-sulfur will have the lowest carbon footprint of any cell chemistry. Current calculations suggest about 65% lower carbon footprint than conventional lithium-ion cells, which is exciting in and of itself. All right, so that's awesome. We have the great idea, the geopolitically realigning level great idea. There's lots of academic papers about lithium-sulfur. But why aren't we there yet? What's so hard? Well, sulfur is an incredibly unruly battery material. In conventional lithium-ion cells, you have the lithium ions intercalating into the structures. And intercalation means that the lithium ion goes in and sets itself in the spaces between the various metal atoms in a crystal structure. And it kind of moves in and out of that crystal structure that way. With the lithium-sulfur cell, the lithium actually reacts with the sulfur. It makes covalent bonds. And not only does it react, but it makes the sulfur change phases twice. Okay? Sulfur starts as a solid, but you add lithium, and it creates polysulfide chains, and those dissolve in the electrolyte. So the sulfur effectively becomes a liquid. And then, as we keep adding lithium, you form Li2S, which precipitates as a solid. And then, when you charge the cell, this happens all in reverse. And on top of that, sulfur is an insulator. So if you tried this with a block of sulfur, it wouldn't really work very well because electrons don't really want to move through the sulfur. So really challenging work. You really make this work, you're really going to grind. You're going to spend a lot of time developing that science. And at Lyten, we've done that. We've created a new material. We make 3D graphene materials. These are entirely new and unique forms of carbon. And we make them out of light hydrocarbons. We take light hydrocarbons, we pull the carbon into the durable graphene, and we produce hydrogen as a side product. This is actually a decarbonizing process. Now, these 3D graphenes have lots of exciting applications. Lightweighting new materials, new forms of advanced sensors, and for me, enabling practical, manufacturable lithium-sulfur batteries. We've shown that our graphenes can hold on to sulfur and conduct electrons to that sulfur. So we have an enabling technology that makes lithium-sulfur possible. This is that new science. Not only that, we can make batteries using slightly modified conventional lithium-ion production equipment. Pouch cells and cylindrical cells, like that's an 18650, which my team made last week. Now, that looks like a really small cell, right? Okay. Anyone here drive a Model S? Oh, come on, guys, you're killing me. Seriously. All right. I have a Model S. It's about 10 years old. I drive around on 7,000 cells this size. This is actually a practical commercial cell size. Okay? You can go bigger, but you can do a car with this. Okay? Now, is that cell going to go into a car this year? No, it's not going to go into a car this year. Even a material as exciting as our 3D graphene, it's not magic. It enables, but it doesn't let us skip the grind. Getting into a cell like we've got is like achieving a Mercury flight. It's an important first step. Okay, it represents a ton of work. There have been thousands of pouch cells and coin cells made to get to that spot. Getting a cell with our new chemistry into cars within this decade is going to be like going to the moon, okay? There's a lot more grind ahead of us. The typically unappreciated, unstoried grind that doesn't scream, hey, I got a paper I've got coming out every month. No, that doesn't happen. It's the grind that requires a cohesive team, diverse team, consistent, substantial, committed funding, and an acceptance of an appreciable level of risk. You know, when astronauts went to the moon, they were considered heroes because we were pretty sure that that was going to work, but not 100% sure. So what does the next few years look like for Lyten? How do we bring our technology to market? Well, we start by making cells like the one I showed you on our pilot line. That's being commissioned today. Then we build a more modest home factory, a few gigawatt hours of capacity, okay? And once we're pretty sure, not 100% sure, but mostly sure that we're going to launch well, we'll build an automotive gigafactory. And everyone keeps telling me, go faster. Okay, how do we go faster? Well, if you're a student of history, you know that the space race was not the effort of a single entity. Government and industry worked closely together as the scale of the effort was immense. Now, if you ever get a chance, go out to Huntsville or Johnson Space Center and have a look at some of those Saturn V rockets that took us to the moon. It'll give you a sense of immensity. Or you can go across the mall out to the Air and Space Museum and spend a few hours there. Once you start looking, you realize that the cast of characters was huge. Now, at Lyten, we know that our plans are super ambitious. They're audaciously ambitious. And we're going to need a lot of committed partners to get this done. We need raw material suppliers, equipment suppliers, and customers to work with us. We need investment partners to raise capital to build the necessary infrastructure. We need government at every level involved, municipal, state, federal, and international partners. And the IRA is a great start and a great help to this process, but it's really only the beginning. All of you could be partners in this endeavor. We'd be pleased to work with you. 1960s, we saw the space race, and now we're in the battery race. And the stakes, again, are geopolitical realignment with a new feature, an impending climate catastrophe that's there with it. So we've got that added bit of desperation to push us to go faster. So we've got to work together. And you know, one of the great quotes out of Hidden Figures is spoken by the NASA boss, and he says, we all get to the peak together, or we don't get there at all. And that's what we believe as well. So we're ready to do this. We're ready to bring partners online to do this. If you're interested, please come talk to us.
Yeah. Okay. So I'm going to ask each of our presenters a question. So first of all, that was an incredible presentation. You're an incredible communicator on technical issues, so thank you for that. And, you know, I guess, you know, the IRA is really thinking about the here and the now, right? Many of the technologies are really focused on the current technologies and how do we get them and build them and get them into cars. Do you feel that the country also needs to think about leapfrogging and maybe so focused on the now that they're not putting enough effort into the types of things that you and other companies like you are doing?
Yeah, that's a great question. Thanks. Yeah, you know, this is like I said in the space race where, you know, people had seen the Russians like put Sputnik up and they'd seen Yuri Gagarin's flight. But they weren't trying to copy that, okay? They were going beyond. And we have to go beyond, right? Because just kind of trying to be a fast follower, that is not a leadership position. That doesn't get us to world abundance. We have to take a leadership role in the new technology. And then everyone is telling me we have to go faster, right? So how do you go faster? Well, that means getting government support to go faster. So if that's what we want, that's what we have to step up to.